Welcome to our final project. Our project is titled as Effectiveness of Meta-Learning with BERT on NLU Tasks. So throughout the semester, we have seen Transformer, and this work has been further extended into BERT, which is a deeply bidirectional model that will map a word into a contextualized word embeddings. And this is a very powerful pre-trained language model that performs pretty well on the downstream tasks. However, there's one issue with it, which is that it needs a large amount of annotated data for fine-tuning. One possible solution towards this issue is meta-learning. And before we directly dig down into meta-learning, I'll first introduce the multitask learning, which is the BERT pre-training process, because there are masked language modeling objective and next sentence prediction objective. And as we can see, the model will be placed in the middle of auxiliary task, but it takes time to converge to the target task. Differently, the meta-learning algorithm will place the model in the middle of every task, which means that a model that is trained with meta-learning algorithm will be able to leverage the few annotated samples, and it will converge to the target task in a shorter period of time. Therefore, our idea is to further pre-train the BERT with a meta-learning algorithm, which is so-called MetaBERT. The meta-learning algorithm that we pick is model-agnostic meta-learning, so-called MAML. And this table is the algorithm that we are using. It's quite overwhelming, but I will explain that. First of all, one auxiliary task will be split into support sets and query sets, which we can regard it as training set and validation set. For every sample task, we will use the support set to update the weight theta. And after this update, we will have theta prime. But notice that at this stage, we are not updating the original MetaBERT parameters data. Afterwards, we will update the theta prime for k steps and end up with another set of theta prime. Later on, we will use the query set to compute a loss value that is used to update the original model parameters theta. This is the memo algorithm.
All right, so let's look at the data set that we have. Our data set consists of 8 tasks. There's SS22, QQP, MNLI, QNLI, COLA, MRPC, STSB, and RTE. We used 4 of the larger tasks in order to pre-train our MetaBERT, and we use the latter 4 smaller tasks to test. However, notice that the smaller tasks are split into 2 sections. That is the train data set and the validation. The train data set is used to fine-tune our model in a BERT-like fashion, whereas the validation test set is used for testing the model. So we have 2 set of experiments. The first set is called the representation evaluation. This is to evaluate the accuracy of the word embeddings generated by our model. When we look at our results, we realize that both MetaBERT and baseline BERT perform better as the data size grows larger. And notice that MetaBERT outperforms BERT in 2 out of the 3 tasks when the entire data set is present. As Tian mentioned at the beginning, one of the ideas behind meta-learning is the ability to use sort of the data sets with low amount of data. However, counterintuitively, when we look at our results, we see that the only time that MetaBERT outperforms BERT when only the 1% of the data set is present is for the STSB 1% data set. The second set is called the few-shot experiments. This is to evaluate the performance of few-shot learning on our MetaBERT model. So when we look at the results, we see that for the RTE task, MetaBird almost always outperforms BERT with few shot and without few shot learning. On the other hand, for COLA task, BERT significantly outperforms MetaBird with few shot and without few shot learning. This is the one task that we conclude that our model is not a good fit for. We also looked for the convergence rates and convergence patterns for MetaBird with respect to BERT. And we didn't really observe any patterns that will also conclude one converges faster than the other. Usually both of these models reach their best performance within 1 or 2 epochs of one another.
Okay, so while we executed these experiments, we came across a number of issues which we resolved for the time being. The first issue that we came across while we began training our model was running out of memory on a Google Cloud virtual machine instance. This is largely because training batch size has a huge impact on the required GPU memory when we train a neural network. And this is because of the fact that there are a large number of parameters that are stored and used in the backward pass to update the model. We solved this by firstly reducing the batch size, and then we implemented a naive version of gradient accumulation where we run the mini batches sequentially and accumulate the gradients. And then these gradients are used to update the model variables at the end of a specified mini batch. We want to try out more techniques and further polish the technique of gradient accumulation so that we do not run out of memory while training on a GPU. Next, we discovered that few shot learning may not be suitable for a regression task because few shot learning contains very few samples to train a particular model, and these very few samples might not contain information about the data distribution to enable the model to predict the next value, which is what the goal of a regression task is. So it can be helpful for classification tasks, but for regression, we need more than these very few samples. Hence, we switched to a few percentage sampling for the STSP task. However, in future, we wish to explore methods which can effectively carry out regression tasks with few shot learning. Thirdly, we fall into a trap of a particular task where the model doesn't learn if it encounters an accuracy value on validation task. It could be because the model is stuck at some local minima, but we certainly have to explore this issue in detail. For now, we ran the experiment several times to get the best output possible. However, in future, we wish to try out different initialization techniques and further explore different architectures for the classifier. This is all from the MetaBird team. Thank you so much for being patient with us.